right, so I guess as people start coming in, I'll start with just some standard administrative stuff. You can do it? Good, okay. So hopefully all of you remember to turn in homework 0 half an hour ago or earlier. The TAs have picked that up already from the drop boxes by 14:04. They're going to the graders. We really want to get them back to you in 1 week. So the goal, and we've got a fair amount of explicit tracking mechanisms set up to help us reach this goal, is that when you turn in homework on Tuesday, you will get the graded homework back into your hands the following Wednesday in discussion section. One of the things that we are doing to try to speed this up, and this is one of the many experiments that we are trying in order to try to make the class scale, is that every homework grade is one of the following integers. 0 means you didn't turn anything in or you broke one of the rules. Or just doesn't make sense what you turned in. 1 means you made a good faith effort, but it was wrong, or you wrote down I don't know. Basically, as long as you turn in something sensible, you get that 1 point. 2 means you're kind of on the right track, but there's some major gaps. 3 means you're mostly right, but there are a few minor issues. And 4 means perfect. 4s are rare. Right? Everything is going to have tiny little mistakes in it. So the hope is that most of the homework grades will be either 2s or 3s. And the reason why we want to do this is partly so it relieves the graders of having to decide whether some strange answer that doesn't look like the homework, the official solutions that are published on the webpage, but still might be correct, but is not quite correct, should be worth 5 points or 6 points or 7 points or 8 points. They can use their judgment and say, yeah, this mostly seems like the right idea, but there are a few small problems, so 3. Right? And the big thing is that all of these grades, the graders' instructions are, every grade that they give, they need to justify with some narrative feedback, which could be as simple as circling the words I don't know and giving you a 1. Or it could be, perfect, or it could be, you forgot the base case, or what if n is equal to 3, or this inductive case doesn't work, or something along those lines. So you get more than just, a crude grade of what we think, but also some reasons why. And one of the reasons we settled on that was feedback from the students in the past semester that what students were generally interested in was not so much the fine details of the grade, but whether they were getting the big ideas. As I said at the beginning of last week, I want continuous feedback on all aspects of the course. So in particular, I would like to get your feedback on how well this sort of smaller scale grading works. The one place where it makes me a little bit nervous is that we are not going to grade exams this way because we want to give, the exam scores will be on a finer scale. Still, in the rubrics, we'll try to explain, if this were an exam question, this is how we would grade it. Okay. Homework 1 is out. It'll be due a week from now. Groups of up to 3 students can submit group solutions. You're responsible for setting up your own groups. The group is defined as whoever's name is at the top of the page. So you don't need the same group for homework 1 as you do for homework 2. You don't even need the same group for homework 1 problem 1 as you do for homework 1 problem 2. There's a mechanism on Piazza to advertise for people to join your group, or if you're looking for a group to join, please use it. We don't require everyone to be in a group. You're welcome to work on your own. But in our experience, there are 2 types of people who work on their own, and it's often difficult for people to know which type they are. There are people for whom the class is easy, and there are people who are lost and don't want to work with other people because they're afraid that they might look stupid. Please, if you are in any way worried about what other people are thinking, what other people, whether other people might think you're stupid, please join a group. Please find someone in the class that you can trust, that you're willing to embarrass yourself in front of so that you can learn from each other by, if nothing else, by them teaching you. The worst thing you can do in a course like this is to sort of realize that you're struggling and then try to go make it through the rest of the semester by yourself. Ask for help in office hours, ask for help in Piazza, send me email, but don't go it on your own. We've got a website set up to do quizzes, but I don't have myself enough together for this class that I'm really, this part of the class I'm teaching for the first time to actually have a quiz, so we don't have a quiz. Whether or not we will ever have quizzes is still an open question. Okay, so last time we started by talking about strings, what strings are, how you think about strings, how you think about functions on strings, like here's the length of a string, here's the number of ones in a string, and the problem 2 in the lab, which we didn't get to, here's the reverse of a string, takes one string in, spits another string out. What I want to talk about today are languages, which for purposes of this class, a language is just a set of strings. And generally speaking, it's a set of strings over some common alphabet, okay? So it's just a set. So I can describe a language using any of the normal notation that we would use for sets. So in particular, there's this lovely set, which is empty, right? It has no strings in it. I can write a singleton set is a set that has one element. In this case, that element is the string foo, which has length 3, but the set has size 1. Okay. In particular, there's the singleton set containing the empty string. This is a set of size 1 that contains a string of length 0. And this is not the same as the empty set. I can define so I can use the standard set builder notation that you might have seen in 173. This is the set of all strings W in sigma star. Sigma star just means the set of all strings over sigma, such that W is equal to the reverse of W. Okay? This is the set of all palindromes. Okay, so I, radar, the empty string, etc. Race car, good, I like that one. Redivider. Strangely, these are all of odd length, so let me throw one more in. Okay. So other things you can do. Given 2 languages, A and B, I can look at their union, I can look at their intersection. There are a couple of other things that, these are so far more or less just things about arbitrary sets, but they're ways of combining sets that are specific to languages. So one of those is concatenation of 2 sets, concatenation of 2 languages. We saw this briefly on Thursday. This is the set of all strings formed by concatenating WX, where W is a string in A and X is a string in B, right? So if, for example, A is the string where every character is a 0, and B is the set of strings where every element is a sorry, 1, 1. Every element is a 1. Right, these are infinite sets. Then AB is, you can write this as all strings of the form with all the zeros come before all the ones and no other restriction. So I can take an arbitrary element of A, glue it to an arbitrary element of B, and that gives me an element of A dot B. And just like with strings, when we concatenate languages, we leave the big dot out unless we really need it to make things clear. Okay? So just as an aside, let's see if we're all on the same page. What is that? So L is a language, and I want to concatenate it with the language containing the empty string. What do I get? You get L, right? Because I pick an element out of the language on the left. There's only one of it. It's the empty string. And I concatenate it to an arbitrary element of L, and what I get out is an arbitrary element of L. And moreover, I can get every element of L that way. All right, here's a more subtle one. What is the language of beer? The empty set. You want to tell us why?
Yeah, because there's no element that can select out of the left.
Right, so I want to concatenate all pairs of strings where the first element comes from the empty set and the second element comes from L. There are no such pairs, so the set of all such pairs is empty. And so the result of concatenating all those pairs is still empty. Okay, again, these two languages are not the same. One of them acts kind of like multiplying by 1, and one of them acts kind of like multiplying by 0. Yes?
But what is the set containing the empty set?
The empty set is not a string, and therefore the set containing the empty set is not a language. Can't add cats to meters. Okay? All right? Similarly, of course, you know, these are commutative. Okay? So you can, it doesn't matter which way you concatenate those languages. Great. So that's concatenation. That's relatively easy. Okay, so there's this, given a language L, you can derive another language from it that is always called L star. And the name of this particular operator, well, the name is spelled K-L-E-E-N-E. Did anyone figure out the right way to pronounce it? The correct answer is there is no correct way to pronounce it. Stephen Claney himself pronounced it Claney. Okay. Stephen Claney's son, on the other hand, is on record as saying there is no language on earth where that string has that pronunciation. Right? In English, it looks like clean. In German, it would be kleine. It's just not, no. So I'm going to adopt Claney's incorrect pronunciation of his own name, and that's as correct as we're going to get. So some people do say clean, some people say cleany. Let's at least say what the guy said himself. So I once had a question from my my master's advisor. So this is how his name is spelled. David is his first name, and I asked him once, do you pronounce that Epstein or do you pronounce it Epstein? And he said, either. Or did he say either? I forget. Okay, so what is L star? So a string W is an L star if and only if one of two conditions holds. One is that W is the empty string. The empty string is always part of the Claney closure of a set. Okay. The other is that I can write W as the concatenation of two strings x and y, where x is an element of L and y is an element of L star. Okay? So this is, of course, a recursive definition. Right? So somewhat less formally, you can define L star to be the result of, it's the concatenation of 0 or more strings in L. Okay, the concatenation of 0 strings in L is, of course, epsilon. What do you get when you concatenate all the elements of the empty set? Epsilon. L is also, you can think of it as the concatenation of any sequence of length 1 of elements of L. Okay, that's a bit convoluted, but so you could also write this somewhat less formally as epsilon union L dot L, union L dot L dot L, union, etc. Okay? If you are a mathematician, you might prefer the word closure here. And what closure normally means, you might have heard in other contexts about transitive closure of a relation. That's the smallest, bigger relation that's transitive. So you can also define L star to be the smallest superset of L that's closed under concatenation. Meaning, if I take any two elements of L star and I concatenate them, I get another element of L star. And now L star is not going to be the only superset of L that has that property. So for example, sigma star, the alphabet star, the set of all strings, is closed under concatenation, even if L isn't just, L may be something more restrictive. And in fact, this is where the this really is where the notation sigma star comes from the set of all strings. The set of all strings is the Kleene closure of the alphabet, considered as strings of length 1. Okay? And what I just said about being closed under concatenation means that you have a couple of other nice identities, like if you concatenate L star and L star, you get L star back. You pick out an arbitrary sequence of elements of L on the left and an arbitrary sequence of elements of L on the right, and you glue them together, you get a sequence of elements of L. So let's try a couple of other things just to see again if we're on the same page. What is the star of the singleton set containing the empty string? It's the singleton set containing the empty string. I take as many empty strings as I want and I glue them together. I get the empty string. Okay? What is this closure of the empty set? No, it compiles. Makes sense. What do I get if I concatenate 0 or more elements of the empty set? Well, I can't concatenate 1 or more elements of the empty set because there aren't any. But I can concatenate 0 things out of the empty set. And what do I get? The empty string. Null star is not null. It's the empty string. The empty string is in L star for every language L. It's right here in the definition. Okay? So I could, grind through, W is an empty star if and only if W is the empty string. Or W is xy, where x is an element of the empty set. Okay, so the second case doesn't apply. Yes?
So in that case, you're saying that always will return a string?
Concatenation of two strings is always a string.
Okay, so
But the strings have to exist. And in the case where L is the empty string, this string x doesn't exist. There are no x's in the empty set.
but then concatenation of zero strings is also
Yes. It's, okay, so again, this is just like, why is the sum of the elements of the empty set 0? Because that's the only way you can get the recursive algorithm for summing things up to work when you add one number. Similarly, the concatenation of 0 things has to be the empty string, because that's the only way to make concatenating one thing come out to the right answer. Okay. Good. So now we've got a sort of vocabulary now for building up different kinds of languages, and so I'm going to define an adjective that you can apply to the word language that means a language built up using the tools we've already seen. Okay, so a regular language is either empty or singleton or the union of some regular languages, two regular languages, or the concatenation of two regular languages, or the Kleene star of some regular language. So again, this is a recursively defined thing. Right? A language is regular if it falls into one of these 5 cases. And in the last 3 recursive cases, of course, those component languages A and B themselves fall into one of these 5 cases, and so on until eventually at every branch of recursion, you hit either the empty set or a singleton string. Okay, so when we want to talk about regular languages, so I could use some, weird notation, right? So here's the singleton set containing 1, and I'm going to concatenate that with the singleton set containing 01, union the singleton set containing 1 and 0, and I'm going to take the star of that, and then I'm going to dot that with 3 1s, and then I'm going to star that, and then I'm going to add the empty string. All right, so this is a regular, union. This is a regular language. Normally, when we talk about regular languages, when we describe regular languages, there's an awful lot of syntactic sugar in this expression that we want to leave out. Specifically, when we talk about regular languages, generally, we don't write the braces, we don't write the dots, and we don't write, for historical reasons, we don't write union as a U, we write it as a plus. So the way I would normally write this language is this. All right? This is a regular expression. Not, as opposed, regular expression is notation. Regular language is the thing that notation describes. Okay, now, it's fairly common to abuse language and, abuse terminology and refer to this object that is written up here in this bottom box as a language. For the same way that, I refer to this thing not as notation for a set, but as a set, as the set of palindromes. But again, if you want to be formal about it, a regular expression is a string that uses, parentheses and pluses and stars and the occasional epsilon or empty set. And that string is a signature, it's a description of a regular language. Okay? So earlier then, when I was talking about these two languages A and B, of course, this language A can just be described by the regular expression 0 star. Yes?
So can you have a regular language that doesn't have an empty string?
Of course. Yes. So if, for example, I just leave out the epsilon here, every string in this regular language starts with 3 ones. It's the concatenation of the language containing only 3 ones and something and some other language. So every string in this language is going to be composed by pulling out an element of this set of size 1, containing the string 111, and this more complicated infinite language. So every string in this language that I've written up here starts with 3 ones, and in fact it's not hard to see that it also must end with 3 ones. Either you use something from this second clean star thing, and if you do, then that will end in 3 ones, or you don't. You might not use anything. The string that you pull out of this second component of the concatenation might be the empty string, in which case these 3 ones at the beginning are also these 3 ones at the end. There was another question somewhere over here, I think. Okay, good. So this is 0 star, B is better known as 1 star, and so this language that I've described where you take some number of zeros followed by some number of ones, you would normally just write that as 0 star, 1 star. Okay? Good. I was told that I should ask this question. I think it's a good idea. How many of you used grep? How many of you know what grep is? So you've probably seen then, I mean, the most basic use of grep, it's a program that allows you to search through a file for strings matching or lines matching particular patterns. And the simplest thing is just to say, you know, oh, I forgot what my password, grep password notes, and it will find all lines in the file notes containing the string password. But at least in some versions, grep actually allows you to search for more complicated things. So it has a vocabulary that looks very much like the notation for regular expressions, where you could ask, for example, hey, could you grep for any strings that start with 3 ones, then alternate between zeros and ones for a while, and then end in 3 ones, which is not exactly what this expression means. But you could write out something that looks like a regular expression and search for that pattern in your file, right? Another place where regular expressions or things like regular expressions show up. How many of you have written any code in Perl? Oh, good. That was the right answer. Unlike Lisp. PHP? I'm sorry. Okay. There are scripting languages that also involve regular expressions because they're used, among other things, to process text files and or web pages. They come in, you do some dynamic search and replace according to some pattern. You know, we were real, say if there were any real hardcore Unix people, I'd say, how many have used sed? Did you actually raise your hand? Yeah. Oh, wow, cool. All right, 1. That was 1 more than I expected. So you can do regular expression matching, search and replace stuff. One thing to be very careful about, though, is a lot of these scripting languages and shell scripts and programs like grep, they use these things called, this object called a regex. Actually, for grep and for things that look like regular expressions that you use in a command line shell, they're normally called globs. These are not regular expressions. They include regular expressions, but they allow you to do strange things like, I think something like this. This allows you to find any word, label that word as word 1, and then look for another copy of word 1, right? So you could find this word because I've got the same word at the beginning and at the end. That's not a regular expression. This is not a pattern. The pattern of strings that match that regex, whose syntax I've almost surely screwed up, is not a regular language. And in fact, later in the semester, maybe a week or so, we'll actually be able to prove that that's not a regular language. It's not something that can actually be done with a regular expression. The important thing about regular expressions is there's no memory allowed. You can't say, oh, remember that chunk and then repeat it later. Okay? And this is actually fairly important. Regular languages are things that you can get from singleton sets by 3 operations. Concatenation, that's the dot. What's sometimes called alternation, this or that, and repetition. But that's it. You're not allowed to remember anything in any sense. Okay. Now, it's probably useful to see a few examples of what you might be able to do. Okay. So, this is strings of zeros. And I can actually think of that 0 as either the string 0 in some larger alphabet or as just the alphabet with 1 character 0. Doesn't matter. Get the same result. All right, so what is this? Good question. Okay, the star binds more tightly than concatenation. Okay, so this is strings of at least 4 zeros, as opposed to this is strings of zeros where the length is divisible by 5. Okay? So the star binds to the last character unless there's something in parentheses. Okay? All right. This is a somewhat more complicated one, which of course I've screwed up already. So the first thing to ask if you're faced with something this complicated is let's just look at the different pieces. What is the first piece? Either it's the language containing 2 elements, the empty string and the string 1. The third piece is either the empty string or the string 0. Again, it's a language with exactly 2 elements. What's that? Actually, I really screwed this up. Sorry, this was not. I'm going to just start over. That's the problem with not using an actual blackboard. Okay, so the first component here is either nothing or 1. The last component is either the empty string or 0. What is the middle component? What is this middle expression? Yeah?
Nothing or 0 and 0.
So and this is important. We need to be very, very pedantic and picky and anal about how we describe these things. That middle expression is alternating strings of 0s and 1s that start with 0 and end with 1 and therefore have even length. Okay? Any number of 0, 1 glued together. So epsilon 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay? So what is the entire expression? Right, so this is alternate 0 and 1. I don't specify how you start, and I don't specify how you end. Or another way of saying this is that there's no substring 0, 0, and there's no substring 1, 1. Right, I never have two characters together that are equal. Otherwise, I don't care. Okay? So the factor, if you will, at the beginning allows me to decide, do I want to start my string with a 0 or a 1? If I want to start with a 1, I just glue a 1 down. If I want to start with a 0, I'll just defer to the second term. Likewise, the last factor allows me to decide whether I want to end with a 1 or a 0. If I want to end with a 1, I just let the second factor deal with it. If I want to end with a 0, then I just glue a 0 down. Okay? Good. Let me try another one here. What's the thing inside the star first? All strings of length 2, assuming we're using the alphabet 0, 1. Right? So if I add the star on it, what do I get? Right. All strings of even length. Right? So can somebody tell me how to get all strings of odd length? Yeah. Sorry? Put a
0 or 1.
right. Or behind, doesn't really matter. Okay. Can somebody give me another expression for all strings of even length? It's not the only way to do it. And this is one of the frustrating things about regular expressions, is that for any given regular language, there are literally an infinite number of regular expressions that represent it, except for simple things. Yeah. Say that again?
So yeah, 2 opening parentheses.
Right.
And then you have 0, 1 plus 1, 0. And then 1 parentheses start.
Close. How do I get the string 0, 0 out of that? Has even length.
You have to do plus 1, 1 plus 2.
Right. So I can do things with, I mean, part of the reason why we use plus for alternation as opposed to a union is to leverage some intuition that we have about algebra. If we want to multiply, we can sort of multiply these things together as though they were polynomials. Yes? There's a question. Plus and union are the same, right? Now, I'm going to try to be very, very careful only to use the union symbol if I'm also explicitly using braces around the sets. Okay, so if you see me adding strings like this, I'm not really adding strings. I'm adding regular expressions. Right? There's no, this is an unfortunate collision with notation. There's not really any sense in which you can take the sum of two strings. But you can take the sum of the sum, meaning the union of two regular expressions, each of which represents a single string. This is, if you decide in the end that you're better off using union just to keep your head straight, fine. Right? Some textbooks, in fact, I think even in some places in Wikipedia, they use union instead of plus. Okay. So let's try to go the other way. how would you get an even number of zeros? This is a little trickier. So any number of ones, but an even number of zeros. Well, here's how I would think about it. There are any number of ones. Okay, so maybe the string starts with a 0, maybe it starts with a 1. If it starts with a 1, I don't care how many ones it starts with. So in fact, I could just say it starts with 0 or more ones. Okay? Now, even. My guess is that I'm going to need, an expression in here that means exactly 2 zeros and any number of ones, and I'm going to put a star around that. Because the way you get an even number is to have 2 and put a star around it. Okay? So I need an expression that means a string that has exactly, arbitrary, the language of strings with exactly 2 zeros. And in fact, because I have that 1 star at the beginning, I can assume, I can even restrict myself to strings that contain exactly 2 zeros and start with a 0. Oh, it starts with 0. Great. So what I have left is strings that have exactly 1 0 that go here. Can somebody give me an expression for 0, 1 strings that contain exactly 1 0? Well, yeah, there's going to be a 0 in it, but what else? There's a 1 star here, and there's a 1 star here. Okay? So, again, the expression in the middle, inside the parentheses, 0, 1 star, 0, 1 star. This is the language of all strings that have exactly 2 zeros and start with a 0. If I put a star around that, this is the set of all strings that have an even number of zeros and start with a 0. Or are empty. And then if I stick the 1 star at the beginning, that allows me to start with a 1 instead of starting with 0. Yes?
Why does it need to start with 0?
This expression?
Yeah.
If I take a string in that language that is not empty, it must be an element of the language 0, 1 star, 0, 1 star, concatenated with some other stuff. The concatenated with some other stuff is part of the definition of star. So if I take an element of the language 0, 1 star, 0, 1 star, that string is obtained by concatenating a string from the language 0 with a string from the language 1 star, with a string from the language 0, with a string from the language 1 star. The first component of that, string from the language 0, there's only one string from the language 0. It's 0. So that must be the beginning. Okay? Whenever you see an unadorned symbol at the beginning of a regular expression, it means all the strings in that regular language must start with that symbol. If I see, a 1 star at the end of the regular expression, it means this string can end with any number of 1s, including no 1s at all. Okay. I'm going to give you one more just to show you that this stuff is actually rather powerful. I'm not expecting anyone to be able to figure this out, but I'm, of course, happy to be surprised. Anyone want to guess what that is? Of course, it's obvious. It's all binary numbers divisible by 3. Yes, that is in fact what it is. Okay, so this is binary numbers divisible by 3. Now, you can reasonably ask yourself, how in the world did I come up with it? And I will admit, I did not come up with it by staring at the screen and writing down little bits. Oh, this is the, what the sub-expressions 1, 0 star 1. I didn't come up with it by thinking about divisibility mod 3. I came up with it by building something called the finite state machine. that accepts all strings divisible by 3, and then I converted that finite state machine into a regular expression using an algorithm that I will teach you. Okay, so it's sometimes easier to build a machine that recognizes a language rather than writing things in this notation that's essentially a recipe for generating language. So this is a distinction that sometimes shows up in machine learning. You have regular expressions are what are sometimes called a generative model. I can take this regular expression and it's a recipe for figuring out all possible things in the particular language. But under some circumstances, I may not want to generate all things. I may just want to decide whether a given thing belongs to my set or not. And then I have what might be called the discriminative model, where I can pass it a string and say, is this divisible by 3 or isn't it? That's a much simpler question because you're not arguing about all possible strings, just this one. And you're thinking about it more or less as an algorithm problem, not as a complicated notation problem. Okay? So in lab tomorrow, we will practice coming up with these things. A little bit more. One thing I do want to emphasize is that there are languages that are not regular. The easiest way to see this, well, for the correct definition of easy, is just to ask the question, how many different languages are there? And of course the answer is there are an infinite number of languages, but this is a math class, and so that's not a good enough answer because there's more than one kind of infinity. I'm not going to walk through the Cantor diagonalization proof because at this point in the course it's a bit of a distraction. But I will want to point out there are multiple kinds of infinity. In particular, there are countably infinite sets, which essentially means you can label each element of the set with a natural number, and you can actually get every element in the set that way. And there are uncountably infinite sets, like the real numbers, where you can't label each element of the set with a natural number and be guaranteed to get everything. Okay? The basic answer here is, the number of languages, I shouldn't really say the number of languages, the set of all languages over some fixed alphabet is uncountable. There's an uncountable number of languages. In particular, in the lecture notes, there's a recipe that associates a language over a one-character alphabet with any real number between 0 and 1. Basically, if the kth binary bit in the binary representation of that real number is a 1, you include the string of length k, and otherwise you don't. And so for every real number, you get a different language. Okay? On the other hand, the set of regular expressions over a given alphabet is countable, because a regular expression is itself just a string over some finite alphabet. In this case, you can think of this string as being a string over the alphabet 0, 1 plus open paren, close paren, star. Right? That's 6 or so symbols. So think of that as an integer written in base 8 with funny looking digits. And this gives you a recipe for associating an integer with every regular expression in a way that guarantees that different expressions will get different integers, and that's enough to show that you can count the regular expressions, even though there are infinitely many of them. Yes?
Does that also apply to the set of regular languages?
Yes, because every regular language is represented by at least one regular expression. Right? Right? So the set of regular expressions is countable, and therefore the set of regular languages is countable. A given, regular language can be represented by many, many different regular expressions, but that means in some sense there are fewer regular languages than there are regular expressions, but still infinitely many. Now this is sort of cool as a proof of concept, but here is an explicit language that is not regular. And the reason that it's not regular is, intuitively, and again, we'll formalize this, is if I gave you a string of 1 billion digits and asked you, is it in this set? Well, you see a bunch of zeros at the beginning and you see a bunch of ones at the end. And if you scan through it, you can recognize at some point I switched from reading zeros to reading ones, and that was the only thing. But the only way to actually figure this out is to count the zeros and then compare that count to the number of ones. So as you read the zeros, you count up. As you read the ones, you count down. If everything balances out, you say yes. But you can't count with regular expressions. You can't count with regular languages. When we start talking about machines, that sense of you can't count will be formalized a bit more carefully. Okay. But there is a larger class of languages that does include 0 to the n, 1 to the n. Some number of zeros followed by the same number of ones. And these are what are called, for largely historical reasons, context-free languages. Okay? Now, regular languages are things you can get from individual strings by gluing them together, by alternation, by union, and by repetition. Context-free languages are things you can get from individual strings by concatenation, by alternation, and by recursion. And in this particular context, you can't always replace, and more generally, you can't always replace recursion with repetition. You can't take any recursive algorithm and without building a data structure in, which you're not allowed to do in this case, turn it into a purely iterative algorithm. Regular expressions are things that are essentially inherently iterative, whereas context-free languages allow a certain amount of recursion. So I'm going to write up the notation for a particular context-free language, and then I will tell you what it means. Okay. So the language involves a bunch of things that look like, capital letters with arrows pointing to other strings of things. B goes to C1, C goes to epsilon, and C goes to 0, C1. Okay, so this is an example of a context-free language. Now, if I want to be, formal about this, this is a context-free language is a bunch of different pieces. Okay, one of the pieces is what's called the alphabet. This is just the set of symbols that you're using to define the strings that the language is over. These are sometimes also called the symbols in the alphabet in this context are sometimes also called terminals. Okay? And then you have a different set of what are called non-terminals. Okay, what are they in this particular case? in this example grammar, the set of terminals is the set 0 and 1. These are the things that only, the symbols that only show up on the right side of those arrows, whatever they mean. And the non-terminals are the things that show up on the left side of the arrows. Okay? Now I have a bunch of production rules which have the form, some non-terminal goes to some string. So this is some non-terminal. And this is some string which consists of either terminals or non-terminals. Okay? So C goes to 0C1, that 0C1 down there on the far right. That is a string that contains the terminal 0, a non-terminal C, and a terminal 1. That's a production rule. The one right above it, C goes to the empty string, that's also a production rule. Okay? And finally, I have a starting non-terminal, which I will always denote S. It's this one that's called S. Okay? So this is just syntax. Okay? So I'm going to have, invariably I'm going to use capital letters to represent the non-terminals, and I'm going to use digits to represent the terminals. And so a context-free grammar is going to be specified by writing down a bunch of rules that say, for each non-terminal, there's an arrow pointing to a string of mixed symbols. And I can have any number of production rules with the same non-terminal. In this case, it just so happened that I always used 2 production rules, but that was really just a coincidence. Okay. Now again, I normally don't write all the syntactic. There's a bit of syntactic sugar here. So I'm going to write the same grammar in a slightly more compact notation. Okay. That vertical line is pronounced or. Okay? And the way that I would read this out loud is I would say S goes to A or B, A goes to 0A or 0C, B goes to B1 or C1, C goes to the empty string or 0C1. Okay? Now what I want, again, this, as I was saying, earlier about regular expressions. Regular expressions are a kind of generative model. They're a recipe for generating all of the strings in a particular language. A context-free grammar is also a generative model. It's a recipe for generating all of the strings in a particular language. And the basic idea is I start with my starting non-terminal S, and then I'm allowed to, at each stage, take my current string, find a non-terminal in my current string, and replace it with the right side of one of the production rules. So for example, I could say, all right, I'm going to replace S with A, because I can. That's what that S arrow A means. And now I'm going to replace this A with 0A. And now I have another A. I can replace it with, I don't know, I can replace it with 0A. The first 0 stays put. I'm replacing here this A with this 0A. Maybe I'll do that one more time. Okay. Then I decide, no, I want to switch to 0C. Then I can replace that C with a 0C1. So 2, 3, 4, 0C1. We do it again. 1, 2, 3, 4, 5, 0C1, 1. And then finally, I'm going to replace the C with an empty string. Okay? That sequence of, replace a non-terminal with a string on the right side of a production rule. That's called a derivation. Okay? Yes?
How did you get,
See an enemy up there, but I'll answer your question first.
how did you get 0008 from 008?
I replaced this A with the 0A. Okay? So at each stage, I pick up one of the Scrabble tiles that has a capital letter on it, and I replace it with a small sequence of Scrabble tiles, which will be mixtures of numbers and letters. Question over here. Yes?
So you can switch out any letter.
That's right. So in this particular case, I always had only one non-terminal that I could switch out. But just for, to give another example, let me give you a slightly different example. Okay? So S goes to either the empty string or S left paren, S right paren. Now here, left and right paren, that's not punctuation. Those are the actual symbols in my alphabet. Okay? I need to be really careful. Okay? So I can go from S, well, I can replace the S with the right side, and now I have a choice. I can either swap out the first S with something, or I can swap out the second S with something. Well, I'll swap out the first S this time. And this time I'll swap out the second S. And now I'll just replace all the rest of the S's with the empty string. Okay? Now, this grammar represents a set of strings, and it's all the strings that you can generate by playing this game in a way that eventually halts. Okay? Anyone care to guess what the language of that grammar is? What strings can be generated by that grammar? Just guess, based on the example. Well, among other things, it will generate. No. Those are real symbols. Those are six letters of the alphabet. If you prefer to pronounce the curvy thing to the right as 0 and the curvy thing to the left as 1, so this string is 001101, great, but it's not the empty string. This is an actual string of symbols. Yeah.
All the strings of...
Yes. This is the language of balanced strings of parentheses. Every open paren is balanced by a closed paren, and inside that pair of parentheses is something called out of the language generated by S, which, by the induction hypothesis, is a set of balanced parentheses. Or, sorry, a string of balanced parentheses. Okay? So these context-free languages, not surprisingly, show up whenever you're talking about complicated expressions where you might have nesting. For example, in your favorite compiler. Because your compiler needs to be able to say things, needs to be able to parse things like this, where, complicated arithmetic expressions, which among other things involve having properly balanced parentheses, right? Right, so this expression is the same as this one if I remove everything except the parens. Roughly speaking, if you ignore some subtleties, Python at a syntactic level is a context-free language. I can write down the rules that will generate syntactically correct Python programs. They may not compile because there are other rules about types and declaring your variables and stuff like that, but at least at the level of pure syntax, your general programming languages are usually context-free as sets of strings. These are, These are also used as models of natural languages. Now, when you talk about natural languages, generally the terminals are not single symbols, but rather single words. And the non-terminals are things that represent kinds of words or phrases. So, I might have a non-terminal called noun that, represents, whether the word is a noun, whereas, noun phrase, it's a bunch of adjectives piled on top of a noun, but notice an adjective phrase might be an article like the, a possessive like my, or a longer adjective phrase followed by an adjective. So this allows me to generate long adjective phrases like, furious, moist, green, severed, timey-wimey in front of my noun, TARDIS. Okay? So you can think of this as kind of a generative model of natural language. Now again, this is not by itself sufficient to define a natural language. And in fact, real natural languages aren't actually context-free. There's a bunch of context-sensitive stuff built into the English language that means I can reasonably say, for example, big red barn, but it sounds really funny if I say red big barn. Those of you who are native English speakers probably red big barn doesn't sound right. And it's because it's violating some contextual rule that native English speakers just don't do. Right? You don't, under the current administration, say, the President of the United States adjusted her hat, because Obama's a guy. But it's at a syntactic level, if you don't dig down into the meanings of those words, it's just a way of generating strings that satisfy some useful properties. Okay, so now there's, because of this ambiguity that you potentially have in this derivation, because I can choose to expand the S on the left, or I could choose to expand the S on the right. At some level, it doesn't matter whether I expand on the right first or I expand on the left first. So in that, if I want to sort of remove that ambiguity from, my proof that a particular string belongs to a particular language, the way that I can do that is by building something called a parse tree. Okay, so a parse tree you can think of as, well, I start with the symbol S, and then I'm going to have 4 children. Let's see, in this case, these 4. And then, if I remember right, these 4. Probably the right thing to do is to start over, because this looks like an ugly tree. So let me try again. I have S, and I can replace that S with 4 symbols. S, open paren, S, close paren. And then I can replace the first S, if I like, with 4 symbols. S, open paren, S, close paren. Then I can replace this S in the middle with 4 symbols. S, open paren, S, close paren. And then I can replace each of the remaining S's with an empty string. Now if I look at the leaves of this tree, and I spell them out in order from left to right, what I'm going to get is the string left, left, right, right, left, right. So this is a parse tree for that particular string. And again, this is something that is, incredibly useful for, particular for natural language applications. You don't just want to know whether a language is a string is syntactically correct or not. You want to know something about that structure. Similarly, it's not enough to know that a string is a syntactically correct Python program. The structure inside that parse tree actually has meaning. So if I look at my example grammar that I showed you earlier, right, with the A's and B's and so on, you can think of the rules as being little templates of parse tree that have one non-terminal at the root and a bunch of children, and that's it. And then by gluing these templates together, I can get a larger tree. So what's on the screen now is the parse tree for the string 000011, using the, derived from the grammar that I showed you at the very beginning, which is, this one. Okay. Using that quote-unquote English grammar, you can get similar sorts of parse trees. Okay, so in this case, this is the parse tree for the sentence, "Your furious green Time Lord barely mangled my dog's trousers." The best I could do. That's the longest sentence I could actually fit in one page. So, clearly this doesn't actually mean anything as an English sentence, but it's syntactically correct. Okay. All right. So, before we go on, I do want to, try to give a couple of examples of, how you figure out what a grammar means and how you figure out a grammar that represents a particular language. So I'm going to start with a very simple grammar. S goes to 0, S1, or the empty string. Anyone care to guess what language this grammar represents? Describes? Yes? Right, this is the strings that consist of a bunch of zeros followed by exactly the same number of ones. Right? How would you prove that? What is always the answer to that question? Induction, right? I have a recursively defined language here, a recursively defined set of strings. If I want to show that every string in this set has a particular property, I would do that by induction. If I wanted to show that every string with that property is generated by this grammar, I would use induction. Notice that was 2 induction proofs. Okay. You've seen this one. This look familiar? Oh, how many of you actually drew a tree for part A of this question on homework 0? Or perhaps a set of nested boxes? Good. That was a parse tree. It's just a different way of drawing the tree. You're drawing it as a set of nested boxes instead of an explicit tree. But that's fine. It's just 2 different ways of drawing the same internal structure. Now, I actually don't know of a brief description of what this language represents, other than perhaps saying, okay, take a binary tree, take a full binary tree, and do a traversal of it. Every time you go down to the left, write a 0. Every time you go up from the right, write a 0. Every time you're in between children, write a 1. Right? So it's sort of like balanced parentheses. If I had done this, left paren, comma, right paren instead of 0, 1, 0, that would have been, all properly nested, ordered pairs that are eventually of empty strings. Okay. We only have 10 seconds left. So I will just tell you what this example grammar is. This is all strings of zeros and ones that start with zeros and end with ones, but the number of zeros and the number of ones are different. Okay? So this is 0 to the n, 1 to the m, where n and m are not the same. And the choice is, do I want more zeros, go to A. If I want more ones, go to B. And eventually I fall down to C, which is just the language at the top of the screen. All right, we'll see more examples of this on Friday. I'm happy to take any questions as you walk out. Thank you.